On the 15th of January, 2022, at 14 minutes past 5 in the afternoon local time, a volcano in the South Pacific produced the largest explosion ever recorded in the atmosphere by modern instruments. Not the largest eruption in history. The largest explosion our instruments have ever measured, far larger than any 20th century volcanic event and larger than any nuclear test. Its name is hungatonga, Hunga Hahaiya Haiya. It is a submarine volcano 65 kilometers north of Tongatapu, the main island of Tonga, in the Tonga-Kermadec Arc. The eruption column rose 58 kilometers. That is not the stratosphere. That is the mesosphere, higher than any volcanic plume ever observed. At the height of it, the volcano produced a series of 4 underwater thrusts that scientists described as a magma hammer, displacing 10 cubic kilometers of rock, ash, and sediment. Loud explosions were heard 65 kilometers away in Nuku'alofa. Ash blotted out the sun over the main island, and small stones fell out of the sky. Many residents were stuck in traffic trying to get to higher ground. 4 people are known to have been killed in Tonga, and 2 drowned in Peru, 10,000 kilometers away, when 2-meter waves struck the coast. 1 more died of indirect causes in Fiji. The reason a volcano in Tonga killed people in Peru is the subject of this episode, and it is not the reason you would expect. Because this eruption did not just make a tsunami, it hit the atmosphere hard enough that the air itself carried the wave around the world. The volcano had been quiet since 2014. On the 20th of December 2021, it began erupting again, pushing particles into the stratosphere. For the next 10 days, it did what shallow submarine volcanoes do, Circean explosions, where rising magma meets seawater and blasts it upward as steam and shredded rock. That word is worth stopping on, because it is named after an event people watched happen. In 1963, off the southern coast of Iceland, an eruption of exactly this kind broke the surface of the sea and built a new island. They named it Surtsey. The mechanism is called phreatomagmatic, and it is violent for a specific reason. Water does not simply cool the magma. Rising magma fragments, water flashes to steam, and the expansion blows the fragments apart again. The magma is usually basaltic, and it shatters into small pieces, ash and lapilli, which pile up around the crater into a cone or a ring. Those piles harden chemically into a rock called tuff, which is why volcanoes of this type are called tuff cones and tuff rings. And the rhythm of it is distinctive, bursts of short, violent explosions, separated by quieter phases, dominated by steam. Much of the wet ash slumps straight back down into the crater and is thrown out again by the next explosion. The volcano keeps re-erupting its own debris. It happens more often than you might think. Vladislav Island in Alaska in 1796, Graham Island off Sicily in 1831, Kaplinhos in the Azores, Anak Krakatau, El Hierro in the Canaries, Taal in the Philippines, and hungatonga itself twice, in 2009, and again in 2021 and 2022. A Tonga Navy crew recorded the first ground-based images of it. Passengers on a charter boat watched surges of it over the Christmas period. By Christmas Day, satellite imagery showed the island had grown by 300 to 600 meters on its eastern side. A volcano building new land in real time on camera. Then it calmed down. On the 11th of January, Tonga Geological Services declared the volcano dormant. 3 days later, it erupted again, sending ash 20 kilometers up, and Tonga issued a tsunami warning. Waves of 30 centimeters were observed in the capital. And the day after that, at 14 minutes past 5 in the afternoon, came the eruption this episode is about. Here is what makes this event genuinely different from every eruption in this series. Krakatoa, in 1883, was recorded by barographs and tide gauges. This one was recorded by everything. Atmospheric pressure waves, Lamb waves, which travel horizontally through the lower atmosphere at close to the speed of sound, were recorded by 50 barographs around the world. That data was good enough to test a new theoretical model of how volcanic explosions generate such long atmospheric waves, and to form the basis of a method for assessing volcanic gas composition purely from distant records. Think about what that means. From a barograph in Europe, you can now say something about what gases came out of a volcano in the Pacific. The lightning was extraordinary too. In the 2 weeks before the climax, a global lightning network detected several hundred to 1,000 flashes at the volcano. Between the 14th and 15th of January, tens of thousands. And in one single hour on the 15th, 200,000 flashes were recorded. Volcanic lightning happens because colliding, fragmenting ash particles and, higher up, ice, generate static electricity inside the plume. The older name for it is dirty thunderstorm. It is not new. The earliest recorded observation is Pliny the Younger, describing Vesuvius in 79, darkness rendered more appalling by the fitful gleam of torches, obscured at intervals by the transient blaze of lightning. And the first person to study it properly went back to the same volcano. Luigi Palmieri, Watch the eruptions of 1858, 61, 68, and 72 from the Vesuvius Observatory, the first observatory ever built on a volcano. It has since been seen above Mount Augustine in Alaska, Eyjafjallajökull and Grímsvötn in Iceland, Etna, Taal in the Philippines, and Volcán de Fuego in Guatemala. There are several ways a volcano makes lightning, and which one dominates depends on how high the plume goes. Near the vent, in low plumes of 1 to 4 kilometers, most of the charge comes from rock simply breaking. Fracturing particles release electrical charge, a process called fract emission. Higher up, in plumes of 7 to 12 kilometers, water takes over. Volcanic plumes carry a great deal of it. From the magma, from lakes and glaciers the eruption vaporizes, and from the ordinary air the column drags upward as it rises. One study found the water content of volcanic plumes can exceed that of thunderstorms. The vapor condenses as the column rises, then freezes. Some eruptions produce volcanic hail. And lightning activity increases sharply once a plume rises above the freezing level, which is the strongest evidence that ice is doing the work up there, exactly as it does in an ordinary storm. Hungatonga's plume went to 58 kilometers. Every one of those mechanisms was available to it at once. There is even a fossil of it. A bolt of lightning reaches 30,000 degrees. When one strikes ash particles inside a plume, it either vaporizes them outright or melts them so they solidify as tiny glass spheres. They are called lightning-induced volcanic spherules, and they can sit in a volcanic deposit as geological evidence of lightning nobody was there to see. 2,000 years later, we counted the flashes. 200,000 in an hour is the kind of number that stops being weather and starts being a machine. The tsunami itself was measured from 22 tide gauges and 8 deep ocean pressure stations, combined with atmospheric pressure records and simulation. From all that, one study reconstructed the initial displacement, 6.6 cubic kilometers of seawater, 90 meters in amplitude, across 12 kilometers. And a satellite instrument designed to measure ozone and water vapor, NASA's microwave limb sounder, which can see through ash, measured what the eruption put into the stratosphere, which is where this story stops being about a bang and starts being about water. A normal large eruption injects sulfur dioxide into the stratosphere. Sulfur aerosols reflect sunlight, and the planet cools slightly for a year or two. Pinatubo in 1991 is the textbook case. Hungatonga did put sulfur up there, about 400,000 tons of it, but because it exploded underwater, it also sent up something else. 146 million tons of seawater, lifted from the South Pacific into the stratosphere. That is about 10% of the stratosphere's entire normal stock of water, added in a few hours by one volcano. And water vapor is a greenhouse gas. So instead of the usual cooling, the water overrode the aerosol effect, and the eruption is calculated to have produced a net warming of the climate system. One study estimated it raised the probability of exceeding 1.5 degrees of global warming in at least one of the following 5 years by about 7%, while stating clearly that greenhouse gas emissions and climate policy remain the major determinant of that risk. That caveat matters. This is a volcano nudging a number that human emissions set. It is not a competing explanation for anything, and the science is genuinely unsubtle. Some studies put the excess water in the stratosphere for 5 to 10 years, influencing winter weather in both hemispheres. More recent work indicates a slight cooling effect instead. In the southern hemisphere, the immediate effect was small cooling of winters and months of spectacular purple sunsets. And in September 2023, the Antarctic ozone hole was one of the largest on record at 26 million square kilometers. That anomalous loss may have been a consequence of this eruption, which is a remarkable chain to be able to trace at all: an underwater volcano in Tonga and a hole in the ozone layer over Antarctica 20 months later. Now back to the tsunami, because it behaved strangely, and the strangeness is the science. Waves up to 20 meters struck Tonga. On the uninhabited island of Tafua, run-up heights reached 45 meters. But waves also arrived in Japan, the United States, the Russian Far East, Chile, and Peru, and in several places they arrived earlier than a conventional tsunami traveling across the ocean could have managed, because the atmospheric pressure wave outran the water. Land waves in the lower atmosphere and gravity waves higher up raced outward at close to the speed of sound. It is worth being clear about what an atmospheric wave is, because the phrase sounds vague, and the thing is not. It is a periodic disturbance traveling through the fields that describe the atmosphere, pressure, temperature, wind. Some travel, some stand still. They range in scale from the smallest sound wave to planetary waves that wrap around the Earth. There are 4 basic kinds: sound waves, compressions, traveling parallel to their own direction of motion; internal gravity waves, which need the atmosphere to be stably layered and travel through those layers the way a swell travels through the sea. Inertiogravity waves, which are the same thing with the Earth's rotation acting on them. And Rossby waves, the enormous slow meanders that make weather systems. Waves like these are not decorative. They carry momentum, and they dump that momentum back into the surrounding air when they break down. In the stratosphere, the transfer runs the show. Planetary waves depositing momentum are what produce sudden stratospheric warmings, the events that reorganize winter weather across the northern hemisphere, which puts the hungatonga eruption in its proper category. It did not just make a noise, it struck the atmosphere hard enough to launch waves of the kind that normally come from continents and seasons. 50 barographs recorded it. And because the record was that good, it became a test case. The data was used to check a new theoretical model of how volcanic explosions generate these waves at all. It also became the basis of a method for assessing what gases came out of a volcano purely from distant pressure records. Consider what that means practically. A future eruption on a remote island, with no instruments anywhere near it, can still be characterized from sensors on the other side of the planet. That is what an event like this buys you. Not just a record of what happened, but a calibration for everything that happens next. And, as that pressure wave passed over the ocean, it pushed on the sea surface and generated waves of its own, a tsunami driven by air rather than by water displacement. That is why a coastal town in Peru, 10,000 kilometers away, received a wave that people were not expecting on any tsunami travel time chart. Existing warning systems were not built for a volcano that shouts. The energy estimates give a sense of the scale, and they disagree enormously, which is itself the honest headline. One study puts the energetic output at about 61 megatons of high explosive, already more powerful than the largest nuclear device ever detonated. Another estimates 100 to 200 megatons. Even its explosivity index is argued about, rated from 4 to 6 depending on the method and the group. It is the largest eruption since Pinatubo in 1991, and the biggest atmospheric explosion our instruments have ever caught, and we still cannot agree what number to put on it. In recent centuries, the only atmospheric disturbance thought to rival it is Krakatoa in 1883. When it was over, the volcano had eaten itself. Surveys found a new caldera about 4 kilometers across, with its floor 850 meters below sea level. A volcanologist involved reported that the caldera walls are still collapsing. 6 to 7 cubic kilometers of debris were spread across 22,000 square kilometers of seafloor in valleys running as far as 50 kilometers from the volcano. And that ash smothered the life it landed on. A research cruise in April 2022, out there to study deep-sea hot spring communities, found the sites near the volcano blanketed in ash, some of it at 2.5 kilometers depth. We spent an episode of the last volume on hydrothermal vent communities and how quickly they colonize and how quickly they die. This is that process, caught in the act, by people who happen to be going there anyway. Scientists suggested the volcano may still be erupting underwater. The eruption has been described as a once-in-a-thousand-year event for this caldera, which means the instruments happen to be watching during a millennium-scale event in the first century when such instruments existed. That is the real significance of hungatonga. Not that it was the biggest, it was not, by volume. It ejected under 2 cubic kilometers of material over 12 hours. It is that a violent water-charged submarine explosive eruption happened while a full planetary observation system was switched on and pointed at it. Krakatoa gave us barographs and tide gauges and a great deal of guessing. Hungatonga gave us pressure waves on 50 instruments, 200,000 lightning strikes in an hour, and a stratospheric water measurement from orbit. Every future eruption will be interpreted against this one, because this is the one we have complete data for. A submarine volcano north of Tonga blew a hole in the seafloor, put a tenth of the stratosphere's water into the sky, rang the atmosphere like a bell, and drowned 2 people 10,000 kilometers away with a wave that the air, not the ocean, delivered.